Good morning, everyone. I would like to welcome everyone with attending today's the Ice and Snow session. My name is Lynn Rouillet from the Norwegian Research Center North here in Tromsø, and I'm co-chairing this session with Erik Hengno. We will have 5 presentations. If you have any questions during or after the presentation, please post your questions on Slido. Choosing the correct session and posting the question there. Then we will have 15 minutes of question and answering the question by the speakers. So it's time now for to give the floor to the first speaker. His name is Yara Yerani. Sorry for my bad pronunciation. And he will speak about deep learning-based delineation of glacier grounding lines. Please, it's you.
Okay, thank you. So the share screen button seems to be up for me. If you could let me share my screen, I will start the talk. Could you maybe make me co-host so I can share the screen? Oh, there we go. Thank you. Okay. All right. Well, thank you for this opportunity, and hopefully you can see the screen now. Sorry if the lighting is bad. It's 3:30 in the morning here on the East Coast, so I'm in the garage so no one else wakes up. But we will do our best here. So yeah, today I'm going to talk about deep learning and its applications in glaciology and grounding line delineation specifically. And I'd like to acknowledge my co-authors that are listed here at the University of California, Irvine and the Jet Propulsion Laboratory. So to start with a broader overview, as we all know, there has been a sort of explosion of observational big data in the geosciences and remote sensing. And it's kind of shifting our bottlenecks in understanding a lot of poorly understood glaciological processes from lack of data to lack of processing in a lot of instances. And to really understand a lot of the poorly understood processes, we need to have more than a few case studies and really look at comprehensive observations across ice sheets and across larger temporal and spatial scales. But at the same time, again, as it's widely known, there has been a huge explosion in computer vision and machine learning, and specifically pixel-level semantic segmentation. And this is really the perfect tool to utilize to kind of bring these two worlds together and get that broader understanding across many spatial and temporal scales that's needed. So with that in mind, the issue that I'm going to focus on in this talk is based on some recent work that we did for grounding line delineation based on double difference interferograms. So grounding lines are basically the boundaries where glaciers go from being grounded on ice to become floating. And obviously this position changes with the tides that move the ice shelf up and down. So that whole range we call the grounding zone as the ice moves with the tides. And this is a key dynamical parameter to be able to keep track of. So as you have warm water kind of eating away at the bottom of the glacier, and you can have retrograde slopes that could lead to positive feedbacks and marine ice sheet instability and all these issues that really need us to carefully track the position of the grounding line over time to better understand the long-term evolution of glaciers and ultimately sea level rise across the globe. So how is this done? This is a notoriously hard thing to do, to map the position of the grounding line over time. So it's challenging to detect from above, from say optical imagery. It doesn't really leave any trace. If you just, if you're on the surface or if you take an image. And the most common way really is through INSAR, by looking at the tidal flexure zone as the ice kind of moves up and down with the tides and figuring out that boundary where the flotation happens. So I can kind of imagine on this side we have the grounded ice, and on this side we have the ocean. And as the floating ice moves up and down, you can see the tidal flexure zone, and the innermost fringe would correspond to the grounding line. But we need to do this at mass scale, and this is usually done with really painstaking manual work that takes a long time to go through enough images to get that broad scientific understanding. So based on some of the past work that we did with cabling fronts, we kind of extended our work to uh, produce an automated pipeline for using convolutional neural networks to map the grounding line position. And so double difference interferograms are particularly noisy. And there's many different textures. If you look at the sample image, you can kind of imagine there's the small scale textures of the actual grounding zone. There's the coherence of the signal. There's if I zoom in on any one portion of this image and not tell you what you're looking at, it's harder to know as opposed to an image. So it's equally hard to train a neural network to get the proper spatial context to delineate the grounding line. And there's just lots and lots of data, and building the proper pipeline to handle that is also its own challenges. So not to get too bogged down in the details, but we basically used a deep convolutional neural network with asymmetric encoding and decoding components. For those not familiar, you can basically think of it as you take these interferograms, you kind of get the high dimensional features that you're interested in, and you kind of build the image by CAD, which is a mask of where the grounding lines are. That's kind of the overview of what's going on here. And some of the key things that we had to do here was to really, if you go back to that issue of multiple scales and interferograms that are relevant to the features, using a series of parallel convolutional networks that work at different scales across interferograms, and really simultaneously get all the features across scales, build that really high dimensional representation of the grounding line, and build an image back out from which we can get the position of the grounding line. So the pipeline, basically we had about 6,000 training images, and splitting that into validation and training sets. And first, we have to basically delineate the raster tiles with the neural network. And because these are done in smaller tiles, kind of stitching them back together to be able to do post-processing and get the right boundaries. And uh, really the step that takes the most work, surprisingly, is vectorizing those raster outputs to get the contours of where the grounding lines are. But the good thing is those contours actually provide uncertainty estimates, because we're taking some raster probabilistic distribution of where the grounding line is and converting that to the vector representation of the grounding line. And finally, draw center lines through those contours that represent the grounding line. Um, so I'll try to be brief with this slide, but basically you can see the ground truth, kind of the training labels, the output of the neural network, and the vectors output. And if you zoom in, the output of the neural network is within the uncertainty uh, with the manual delineation, which is the ground truth. And in fact, this is true not just in this one example, but in all cases. So if you look at the mean uncertainty, it was about 4.5 pixels given by the neural network. But the mean difference between the manual delineations and the automatic delineations is about 2.3 pixels. So we are within that error bound. Um, and in fact, the mean difference is smaller than if you compare the performance of different humans trying to do the same task, even though they have a narrower spread in case of things that are completely off the location. But this is basically comparable to the performance of a human being, and it's more consistent because it draws the same line at every place. Um, so just briefly, it was also interesting to see, okay, how is it actually doing this? And looking at some of the activation maps, which is telling you where the neural network is picking up the signal from the interferograms to get the grounding lines. You could see that as you kind of go along, you start with the inputs, the real and imaginary components of the interferogram, and you kind of initially the neural network layer 5 is kind of getting raw features that don't exactly represent to the grounding lines. And then as you go all the way up to layer 16, which is just these serial layers of convolutional networks, it's getting bits and pieces of the grounding line. But because of that kind of multi-scale problem, you can't get the whole image. And it's really the implementation of this parallel system that we put in compared to, say, the Calvin framework that we did. Looking at different scales in parallel, all of a sudden the grounding lines just pop out. And interestingly, also the two sides, the ocean side and the ground side, have an asymmetric activation map, which tells you how it gets the right side of the flexure zone in the French patterns to get the grounding line. So, this was working well, and we actually delineated the entire coast of Antarctica from available Sentinel-1 image data from 2018 all across Antarctica. So this was about 23,000 interferograms with 6-day and 12-day intervals. And in total, this took about 21 hours. And if a human were to do this, it would take about 7,600 hours to give you a sense of the scale that's possible with this. And it's also interesting to look at this scale some of the different spreads on different coasts and the season, the variability over time, which we don't have time to get to here, but kind of jumping to the science takeaways before I finish. Basically, what we observed was vastly different from what you would expect given basic hydrostatic equilibrium and what you expect the position of the width of that grounding zone. So if you remember with the tides, as the position of the grounding line moves, given hydrostatic equilibrium, you expect you can calculate the width of that kind of fluctuation over tidal cycles. And what we actually see is about an order of magnitude, or more precisely 13.3 plus minus about 4 times larger than the observation. So this is really interesting. There's some discrepancy between observations that are not just based on our observations, but also has been observed in other studies where what we observe doesn't match with hydrostatic equilibrium. So what's going on? There is theoretical studies that actually say not assuming a hard bed and kind of rigid ice, you can get some of these numbers. And these studies, for the first time, doing a mass scale delineation of um, all the widths of the grounding zones can actually provide the evidence to corroborate or negate some of these theoretical frameworks. And this is important because if the grounding zone is actually much wider than previously thought, that means the warm water can actually intrude much further under the ice and melt it much faster. So at the end of the day, this is useful information for ice ocean interaction and ice sheet modelers to be able to use this. So just to finish up, I'll just say that while this is working well, and we actually published this work in Nature Scientific Reports this year, there are still some aspects that we would like to work on going forward. One is introducing an element of temporal dependency and memory to the system, where if you know where the grounding line was at one point in time, using that information in the next time step. And lastly, to encode vector representations of the geometry of the grounding line in the neural network instead of having to go back and vectorize the raster output, because that's the most time consuming and computationally expensive step of this process. And I'm happy to talk to people about these ideas. There's some ongoing work in this, and I think that would really be the next big improvement in this. So with that, I'll kind of end it. And yeah, happy to. Oh yeah, and the code and data is available if you go to the publication. There's the GitHub repo. You can check out the code. And yeah, I'll just leave it at that. I see there's one question. I don't know if there's time.
We will take the question afterwards.
Okay. Okay, sure. Sounds good.
Thank you very much, Yara. I forgot to mention before that when you write your question, and the first one we got here is right, please write the name of the speaker you want to an answer from. So we move further to the next presentation. The speaker is Thomas Nagler, who will speak about the use of Sentinel-1 INSAR and offset tracking for ice sheet velocity mapping. Thomas.
Yeah, please, can you just give me the presentation mode?
I am not able myself, sorry.
Okay, thank you, Lynn. In my presentation, I will give you an overview on the recent developments on the synergistic use of Sentinel-1 SAR interferometry combined with offset tracking for an improved ice sheet wide velocity mapping. And this is a collaborative work of the NBO team, and you see the different co-authors in the slide here. In my talk, I will give an introduction on the state of the art of ice velocity production using offset tracking and the improvements using a new product, the enhanced timing annotation dataset for ice velocity retrieval. I will show the improvements through the application of SAR interferometry velocity retrieval using TOPS mode Sentinel-1 data, and finally towards the combination of SAR interferometry and offset tracking for an improved ice velocity product. So this slide shows you the state of the art, what we do currently in Antarctica with Sentinel-1. Due to the acquisition strategy of Sentinel-1, we have a continuous monitoring of the margins of Antarctica almost every 6 days. You see on the right side the acquisitions of these continuous monitorings. The interior of Antarctica was acquired during one campaign in 1617 and is currently not monitored continuously. Similar strategy has been done for Greenland, where we are generating also ice sheet wide velocity products using offset tracking. But we have also monthly products, and they are improving from the launch of Sentinel-1 from in 2014 onwards to now, so that we are having more and more a complete coverage of these ice sheet. So what are the characteristics of the offset tracking product? It has a fully providing fully constraints of the flow vector, so it has the range and azimuth components, which means that we do not need crossing orbits in order to look for the velocity vector. It is streamlined for unsupervised fully automatic processing, and it's also suitable for operational monitoring. And this product is actually done also within the Copernicus Climate Change Service operationally. It is very efficient in capturing the fast moving ice flow of the outlet glaciers. We have time series for monitoring of the temporal variation. And one example you see of one of the outlet glaciers of Jakobshavn Glacier, the high temporal variability along the central flow line. And we see here this seasonal variation and also the annual trend during the last decades of these outlet glaciers. And Sentinel-1 gave here really a big impact in monitoring these sub-weekly cycles. This product has also some issues, so it's quite sensitive to ionospheric effects, especially ionospheric strikes. And they are affecting, in particular, the retrieval in the slow motion where we are observing this. And also, we are needing a kind of reference for calibrating the velocity. And here we're using stable areas, primarily at the boundaries of Greenland, where rock outcrops and so on. Now, this is, of course, a special issue when we have long tracks which are not connected to the boundary. Then this calibration has an issue, and there was just a new product coming up which has an impact on the quality of these parts. And this is a kind of enhanced timing annotation which is given pixel by pixel and gives the time delay due to different reasons. And one is, for example, tropospheric time delays. So ECMWF data are taken into account to calculate this. Then also solid earth tides are taken into account, and also ionospheric effects, as well as the SAR processor. And I just show one example here over Greenland, the long data track. On the right side, you see the output of the offset tracking in light of only the line of sight, which shows obviously quite a significant bias and needs to be calibrated. When we are using this with the annotation of the ETAT product, this bias is automatically reduced on the pixel by pixel basis. And as a reference, we look on the right side, the multi-annual reference line of sight velocity. And this product, the ADAT product, shows that this bias is widely reduced, and this is a significant improvement in the retrieval of this part. We see here also the histogram of the difference between the offset tracking results in line of sight with and without ADAT correction, and you see that the bias is really almost zero-centered. Now, but still in the center of these of the ice sheets with slow motion, we have a problem due to this ionospheric strike, which cannot be taken into account by the ADAT product. And here we are looking to the sound interferometry mode. And this shows the problem when we apply sound interferometry of TOPS mode over moving ice, that we are observing phase jumps on the burst interfaces of the different subspots, but also on the burst itself. And this, of course, hampers the time, the phase unwrapping, and really causes issues when we just use an input of the interferogram like this. And we developed in an ESA study together with TTU a method where we are using a motion compensated co-registration of the master and slave bursts, and the ice velocity motion used for this is taken from the offset tracking, the multi-annual offset tracking. And here we show the overall processing line of this ice sheet wide velocity product. To generate it, I will not go into detail for the different steps, but I will highlight some of the key steps here. The major thing is that you need a smooth offset tracking velocity, which is transferred into slant range geometry and is used for co-registration. And this reduces almost all the phase jumps at the burst interfaces. Another point is phase unwrapping of long data takes, which can be several slices, so 1,500 kilometers or even longer across the complete ice sheet. Then we are masking out aliased regions. So we know at seedbed that fast-moving glaciers and sharing zones can be problems and cause decorrelation, but also snow melt or snow accumulation can have even over 6 days decorrelating the phase. We need a few reference points for the phase calibration, and then, of course, to combine the different tracks to form an overall map, we are applying a least squares approach. There are some limiting factors, as I mentioned before, decorrelation due to snow melt, snow drift, and accumulation. There can be some ionospheric and tropospheric effects available. Phase unwrapping errors can occur, especially when we are close to sharing zones, and that we can have this issue. And then, of course, one of the pre-limitation in order to have this is the kind of acquisition plan to provide the ice sheet wide coverage of crossing orbits. And this is actually not given all the time. So you see here the acquisition of the winter campaigns. So this is in general mid of December until mid of February every year, from 2017 to 2020 onwards. And the different colors show you the availability of ascending, descending pairs coverage. So always 6 days repeat coverage is taken here. And in gray, these are the areas where we don't have a coverage of crossing orbits. And in earlier years, we have quite large areas not covered by crossing orbits. While in 2020 and 21, we pushed ESA to adapt the acquisition planning to extend the crossing orbit coverage over Greenland. And we have now almost at least one acquisition of crossing orbits available. There are only a few gaps left shown in gray. Now, using this crossing orbits technology, we can generate these maps. So we used here the acquisitions of the winter campaigns from 18 to 21. And the gaps are here visible where we are lacking some data. So this is even over 3 winter periods, we don't have a full coverage on this. Then we have also some gaps at the very fast outlet glaciers. The product has a resolution of 50 meters, while the offset tracking product would have 250 meters or 500 meters, depending on the processing. When we are looking, for example, to the quality of this, we made here a profile across the ice divide. At the ice divide, the velocity should be 0. And we are very close here to the no motion level, while the other one shows the quite high noise of the offset tracking product. And we validated this for a local region by data which were acquired by Christine Wittberg and were published in the Cryosphere just recently. And we intercompare this in this small area here with a couple of GPS stations. And although it's not covering the same time interval, we have a mean difference of below 5 millimeters with a standard deviation of below 2 millimeters per day. Now, in order to complete this coverage, we can also use those acquisitions where we have only one viewing geometry, so ascending or descending available. And we are using here the offset tracking, the flow direction from the offset tracking in order to extend the inside velocity. This is still an improvement against the offset tracking velocity retrieval. And what we are assuming here is stable flow lines. The velocity is derived from one viewing geometry using INSAR. And using this technology alone, we would have, of course, some data gaps along the ice divide itself. But as you see, compared to the previous crossing orbit part, we can process backwards in time and increase the extent of this high quality product. The center image shows you the flow direction derived from the multi-annual offset tracking product, and the color wheel gives you just the flow direction in degrees, and 0 would be north, so that's the reddish colors. Now
You
we
have
can
2 minutes left.
Okay, thank you. So we can combine the Greenland ice velocity products derived from the different techniques just presented. So inside crossing orbit velocity would have the highest priority, complemented by the single view inside line of sight velocity from offset tracking. And for the very fast glaciers where INSAR is in generally decorrelating, we are using the offset tracking velocity results. And this is combined together using a least squares approach. Now, what do we expect in the future to further increase the quality of the product? And here we are looking for the upcoming L-band missions. And we selected here one region of the Negis ice stream to simulate the expected fringe pattern of Rose L. Rose L, there will be 2 satellites in orbit operating closely with Sentinel-1 in the same orbit, and therefore we use the orbit geometry of Sentinel-1. And the big advantage of Roselle operating in a 6 days repeat would be that we are bridging the gaps of the sharing zones, which are decorrelating at the C-band. So we are extending significantly the coverage of the interferometric velocity retrieval. And another example, or another advantage would be that it's less sensitive to temporal decorrelation due to snowdrift. And in slow-moving areas, we can combine, of course, both frequencies, so Sentinel-1 and Rose-L, in order to improve the product. Now to the conclusions. So we showed that Sentinel-1 TOPS mode interferometry using crossing orbits can be applied to generate high-quality ice velocity products. And it has a higher spatial resolution, in this case of 50 meters, and it's less affected by ionospheric noise. We can combine the INSAR line of sight displacement with the flow direction of offset tracking in regions where we only have one acquisition from one path. And this is, of course, also a major improvement, but this assumes to have stable ice flow velocities. Then INSAR crossing orbits combined with the INSAR with offset tracking flow direction and offset tracking themselves can be combined to generate an optimum ice velocity product. And this is just a development at NVO, also to go on for more operational use. And I think, or we think, that the combination of Sentinel-1 with upcoming L-band sensors like ROSEL will be very interesting, but also the combination of the right-looking Sentinel-1 with the left-looking NISAR will offer a very interesting constellation for monitoring the ice dynamics. Thank you.
Thank you very much, Thomas. Perfectly just on time. We will now move to the next presentation from Romain Milan.
Yes.
Who will speak about comprehensive ice velocity and thickness mapping using a combination of SAR and optical sensors. Thank you, Romain.
Yeah, so I'm waiting for the share button to pop up. I don't have the sharing rights up. Here it is. Okay. Oh. Hi everyone, so I'm Romain Milan and I'm going to present you the work that I've been doing during the past 2 years at the IG laboratory in Grenoble, which aim at mapping surface flow velocity of mountain glaciers and use this mapping to map ice thicknesses globally. So the ice thickness is a fundamental variable. It allows you to have the total volume of the ice, but more importantly, the ice thickness distribution, which is fundamental to have a good temporality in the projection. At the moment, there is only a very small portion of the glaciers that have been mapped, and those in situ measurements are really limited spatially. So most of the time, it's only one line or a point. So because of this lack of direct measurement, there is an increasing international effort to develop inversion approaches to reconstruct ice thickness at regional scales. So it started with some simple approaches from area scaling, and it rapidly evolves into Glenn flow laws and the use of mass conservation, and more recently, a neural network. However, those methodologies are still limited because of the use of simplified glacier geometry that creates artifacts at glacier boundaries. You can see here an example of an ice cap in Baffin Island where you have 0 thicknesses at the boundary of glacier basins. And moreover, these methods are also limited because of the lack of input data. And here I'm going to specifically be interested in the lack of surface velocity data. So the surface velocity is a fundamental variable because, of course, it allows to monitor the glacier dynamics, but it also provides an important information on the distribution of the ice thicknesses. At the moment, the ice velocity have not been widely used for ice thickness mapping of glacier because there is the resolution is not currently sufficient to map a large diversity of glacier, going from small glacier in the Andes up to large marine terminating glaciers in the Arctic. And also you can see on this map of the state-of-the-art its live ice velocity coverage that many regions have not been mapped, specifically in the Andes or in the European Alps, where it is crucial to have ice velocity data, for example, to map the ice thicknesses and, as a consequence, the water reservoirs. So the goal of this study was really to provide a new global coverage of glacier surface flow velocity at a resolution that is sufficient for glacier modeling, and also to monitor the ice dynamics, and to use this new product of ice velocity to re-estimate the volume of the world glaciers. So at IG, we developed a processing chain that allows to calculate ice velocity at the scale of entire mountain range. So it's decomposed in 3 main modules. You have the first module that is going to download all available images within a region of interest. So we developed the processing chain to work with Sentinel-2, Landsat-8, and for the radar, we use a Sentinel-1 data. So this first module download all image, assemble all possible image pairs, and then we do some basic filtering on optical data to enhance surface features. And then we move to the ice displacement calculation, which is the most time-consuming part. So it's based on the MCOR algorithm from the Jet Propulsion Laboratory that was wrapped out in a Python package. And when this is done, we move to the post-processing part of the chain. So basically, we translate the ice displacement into ice velocity. We do some median filtering to remove outliers, and then we calibrate the ice velocity. So basically, we mask out the glaciers. We calculate for Sentinel-2 an average value of offset on stable ground. For Landsat 8, it's a linear ramp, and for Sentinel-1, it's a quadratic fit. And then we correct the full offset map so that we have the Vx and Vy component of the velocity field that is centered on 0. So when this is done, we have a multi-temporal product, and we do a pixel by pixel weighted average, which gives us a comprehensive ice velocity mosaic. So we run the correlation at a sampling resolution of 50 meters. And so we combine all radar and optical data over the years 2017, 2018 for this study. So we validated our ice velocity map over the European Alps. We used the dense GPS networks in the Mont Blanc area. You have some example of GPS here on the Argentia Glacier. And we also used some GPS point in the Austrian Alps, which you can see on this map. And so we found an average difference between our composite mosaic and the GPS of 6 meters per year. So on this map, you have a comparison of the coverage of the EATS Live and the coverage that we did for this study. So you can see that we were able to improve the coverage, the world coverage. We mapped all glaciers in the Andes, in Central Europe, all subantarctic island, and New Zealand. And again, we provide the sampling, the mosaic at a sampling resolution of 50 meters, which allows us to capture a much larger diversity of glaciers, as you will see in the next slide. All right, just before, here on this slide, I want to stress out the high value of the Sentinel-1 radar data, and specifically for glaciers in the Arctic, where it was really a game changer for us to have a comprehensive mapping. You can see here an example on Penny Ice Cap in Baffin Island. You can see that we were not able to capture any of the interior of the ice cap with Sentinel-2. With Landsat 8, it's a bit better, but you can see that it's really noisy, and really the only sensor that is able to capture precisely the pattern of the surface velocity is Sentinel-1. You can see these really nice ice streams that extend up in the center of the ice cap, which are going to be essential to map ice thicknesses, as you will see later. So here you have an overview of the large diversity of glacier that we were able to map. As you can see, we mapped small glaciers. For example, here you have glaciers in the Andes that are less than 1 kilometer large sometimes. You have the Mont Blanc area in the French Alps. And here in the middle, we were also able to map a marine terminating glacier. You have the Penguin Glacier in Patagonia here that flows at more than 12 kilometers per year, which is only comparable to Jakobshavn in Greenland. And finally, at the bottom, you have some example of glaciers flowing out of ice cap in the Russian Arctic. Okay, so how did we improve the local coverage? How did the resolution really make a difference compared to what exists? So here you have a comparison between the EATS Live on the left and our composite mosaic on the right. And you can see that for the case of Patagonia, for this example, our velocity mapping really improved the spatial pattern of the velocity field, which was only possible by using a wide variety of sensors, so Sentinel-2, Landsat 8, and more importantly, Sentinel-1. Yep. And here you have another example here for the Khumbu Glacier here in the Himalayas close to the Everest region. And you can see that the use really of a smaller sampling resolution really allows us to capture really smaller scale features. You have the icefall of the Khumbu Glacier that didn't appear in previous mapping, but that we were able to capture here. Okay. So now I'm going to move to the part on the ice thickness calculation. So we used a simple approach based on the shallow ice approximation, which links the ice thicknesses with the surface velocity, the surface slope, and the creep parameter of the ice, A. So we use the surface velocity here as an input for the surface slope. We use a combination, again, of optical and radar data. We use a combination of Aster global DEM and the Tendemix global DEM. Basically, what we do is that we calculate the slope roughness, and we combine the two DEM so that we have the slope with the smallest roughness. And in the Arctic, we use, of course, the worldview Arctic DEM. So once the slopes are calculated, we also add an additional smoothing step. So we smooth the slope with respect to glacier width. So if you have a large glacier, we're going to have a lot more smoothing than if you are on a smaller branch. Okay. So we validated our model over the Alps because we have a large variety. We have a lot of ice thickness observation. So basically, it's really simple. What we do is that we run the thickness model and we calibrate it with only 40% of the data. Then we compare the results with the remaining 60% of the data. And we found a standard deviation of 50 meters with a mean difference with in-situ observation of 15 meters, which is comparable to what we obtain if we use all in-situ data, and meaning that we do not particularly overfit the observations. So here on this big table, you have the volume of all glaciers of all RGI regions that we mapped with this approach. And here on the right column, we have the difference between the 2019 consensus estimate from Farinotti. So on average, if we look at the total volume, we are on average 12% lower than what was estimated before. But we noticed that some part of the glaciers were already accounted in the ice sheets. So if we remove the glaciers that were accounted in the ice sheet, we have a sea level equivalent that is 30% lower than what was estimated in the past. So those are regional differences, but it does not highlight the high local differences that can be seen on the thickness map. And this is what I'm going to show you next. So here you have an example.
2 minutes left.
Okay, so here you have an example of the ice thickness over Vatnajökull in Iceland. So you can see on the left, this is our ice thickness mapping. So really our regional approach allows us to have a coherent ice thickness map that does not have the high artifacts that are present in the state-of-the-art estimate. Here you can see the zero ice thickness in the middle of the ice field, and this lateral artifact due to the simplified flow line approaches. You again have this example on Penny Ice Cap. I really like this example because we can really see this deep valley that extends inland of the ice cap, which was only possible using a regional inversion of ice velocity mapping that is not present here again in what existed before. So in terms of water resources, we also look at the water reservoir within 6 watersheds where the glacier contribution to runoff is more than 5%. And again, we could find some large differences. I'm not going into details because I don't have much time, but in the Himalayas overall, we find larger volume because we have more in-situ data to calibrate the inversion. And on the contrary, in the Andes, we found a lower available water resources in glacier, which is important in terms of future prediction of available fresh waters for this highly densely populated area. So as a conclusion, we have a new product of ice velocity mapping globally at a resolution of 50 meters that combines both optical and radar data. So we use this new ice velocity mapping to re-estimate the volume of the world glacier globally. Our results show drastic differences, especially with a previous estimate that will have a large impact for the future prediction of glaciers. And we hope that this new data set that will be made available publicly soon will open doors to new methodology for future prediction of glacier evolution, but also for to model ice thicknesses. So yeah, thank you.
Thank you very much, Romain. We'll move to the next presentation from Jérémy Mouguineau about continent-wide interferometric surface mapping of Antarctic ice velocity and new possibilities offered by Harmony and Earth Explorer 10.
Thank you, Lynn. Yeah, share button, it's good. Can you see my screen? I guess it's good, but it's not. It's already the conclusion. Let's go back to the first slide. Up. Okay, does it work? Yes.
All good, yeah.
Okay, so I want to present my result on mapping Antarctica ice velocity using INSAR data. So very similar to what Thomas showed for the Antarctic, the Greenland ice sheet. And then I want to move to the possibility that will be offered by the Harmony mission. So it's an Earth Explorer 10 candidate. So this work has been done in parts at the University of California and in parts at CNRS in France, and also with collaborators from the Harmony missions. So just I come back to some of the results that Thomas showed. So usually when we map motion of the ice over a large area like Antarctica and Greenland, we use spectral tracking, which is cross-correlation between images. So we can do that on SAR amplitude images or using optical data. The limitation with this technique is the resolution is mainly the resolution of the sensor. There can be also other limitation, but this is the main resolution in terms of accuracy and precision you can get on the measurements you do. So here in this example, this is the traditional map of Antarctica that was published by Eric Rignot in 2011 and updated over the years after, that is published at NSIDC, and it's mostly based on cross-correlation techniques. And on this table, I listed the mapping precision you would get for the nominal cycle of the SAR sensors if you can map displacement at 0.1 pixel precision. And you see that basically what you get is a precision around 5-10 meters per year in displacement. So you're not really able to capture what's going on the slow-moving portion of the ice. So this is what I wanted to show here. Here is the cumulative distribution of the speed that you find in Antarctica. And you see that actually 60% of the ice sheets is flowing slower than 10 meters per year. And that means that for the 60%, you don't get very precise mapping of the ice flow. And the solution that we all know is that with SAR, we don't not only have signal from the images and cross-correlation, you have a coherent signal, and so you can rely on the phase to map displacement, and it's much more precise. So this phase is sensitive to the geometry. Stereoscopic effect you will have between two orbits that don't fly exactly at the same place, and so there's different views, and you get a signal from this, and also the phase change due to the motion of the surface that you can map. If we assume here, this was for an example, that you can actually map this displacement of the deformation of the ground at the resolution of p radian, so alpha cycle, and I think we can often do better than this. You would get precision that are on the order of 10 centimeters per year instead of 10 meters. So you have a huge improvement in terms of the accuracy and the precision of your measurements. We didn't move toward this approach in the past because it's actually difficult to put in place over such a large scale. There is difficulties in area of fast flow, for example, aliasing. So there's too many fringes, and then you have issue in wrapping your face and retrieving motion. And also you need a more complicated way of observing the ground because you're sensitive to only one component, and then that means you need, for example, ascending, descending tracks, so view with different geometry, so you can reconstruct at least the 2D motion of the displacement. So this is what we have done here. We have moved to the phase information, and to do this for each track, we started to calibrate and unwrap the phase. So first we would remove just the flat Earth interferometric phase that you get on an interferogram. We would correct for the topographic effect that is in the phase signal using an external DEM. So here we use a 30 meter StandMX DEM that is, and we corrected in some places using the Aster DEM, for example, on the peninsula. So this is very similar to the new Copernicus DEM that is available, that is now publicly available. And then the remaining signal would come from displacement, and we would unwrap this using the algorithm developed by Goldstein, Zepker, and Werner. That is a very conservative algorithm. There is unwrapping algorithm now that actually are probably more efficient or would cover more ground, are able to cross some region of low coherence. But this one, it was very conservative. It was rapid and robust. And so we use that, and this way we minimize the phase jump errors that we would get, but at the expense of getting less spatial coverage. Here, yeah, again, a correction. A second correction we did only for L-band. So L-band has the issue of being at lower frequency, and so it's much more affected by the ionosphere. When you go through the plasma that is composed the ionosphere, you're close to you're getting closer to the plasma frequency, and then it creates a delay on your phase. And this can be seen on the graph on the right, where we plotted ice velocity along a track from Elos pulsar. So on the top, you can see the black line that is very noisy. This is the speckle tracking result of ice velocity, the first map I showed in the presentation. And all these color lines correspond to different tracks of Elos pulsar going exactly along the same orbit. And you can see huge differences in the speed you would retrieve if you use that without ionosphere correction. So what we did, we used a split bandwidth technique that was developed by Liao, and we cut the pulsar signal into two parts that would be at different frequency. And so the effect of the ionosphere that depends on the frequency you're using will be different. And then we can actually correct for the phase shift that is introduced by the ionosphere. So on the bottom, on the same cross-section that you saw, velocity against distance along the track, you see that this phase shift is actually well corrected, and we get a nice signal. You can see also the same result in terms of interferogram that are on the bottom. So the original interferogram that show a different signal. There is the signal from the motion, but there is an additional signal from the ionosphere. The ionospheric phase screen, so that we retrieve from this split bandwidth technique, and the corrected interferogram that looked exactly the same between the different tracks. So this was applied to 500 Elos tracks, and to correct for Elos pulsar. Technically, it would have been good to look at the C-band sensor, but because it's at a higher frequency, the effect of the ionosphere is much less. So it was too much of computational work to do this for all the C-band, so we didn't do it here. But this could be done in the future if we want to. And here, this is all the unwrap phases that we use to compose this 2D map of displacement. So we use NVSat ASAR with a set of ascending, descending tracks, a large data set of RadarSat-2 tracks that also cover the interior of Antarctica. And RadarSat-2 also provide ascending and descending tracks. There is LOS Pulsar at L-band that I talked about in the previous slide, that only provide ascending tracks and need to be combined with also data. So we get the another direction, another view for the displacement. And then older data from ERS and RadarSat-1 that was used to fill some gaps, for example, on West Antarctica. So for example, the ERS data set that is done over 1 or 3 days that get good correlation in these places where it decorrelates very quickly. So the result of this map is shown here on this graph. So this is what we can cover with all this data set in terms of interferometric phase over Antarctica. So we can see that we miss the fastest flow, or the region where there is more fringes because it's too fast, too large gradient in speed. And this map was assembled using ice flow parallel surface. So we have 2 components, and we have to assume something for the third one. And we just assume that the ice is flowing parallel to the surface, and then the vertical component is given by an external DEM. So here it was again tandem X. DEM over Antarctica that would give you the component, the vertical component. So using it, we can cover 71% of Antarctica with phase. It corresponds to the region where actually the speckle tracking is the signal to noise ratio for speckle tracking is the worst. So it's a good thing. And as I said, there is limitation on the coast due to decorrelation, temporal decorrelation, and aliasing of the fast flow. Same graph as Thomas showed for kind of same graph as Thomas showed for Antarctica. So this is the error in flow direction. So on top you have the flow direction with, I think it's almost the same color code that was showed earlier. Where color would show the direction of the flow. So the one on the left is the flow direction that was retrieved with tracking techniques, where you can see it starts to be very noisy when you're getting closer to the interior, closer to the ice device, where ice is flowing at a very slow pace. While on the left, you have the same.
Jeremy.
Sorry?
Sorry, 2 minutes left.
2 minutes. Okay, I'll try to go quickly. And on the left, there is the same map using only phase, where you can see the device have, much more defined and much more precise. And in terms of errors on the direction, there is this cumulative graph on the bottom, where you can see that actually now 80% of the Antarctica can be mapped at a precision less than 10 degrees, where it was only 25% before. Okay, so this map has been combined with speckle tracking to get a complete map, as is published on NSIDC. And then what's next? So now we have a good knowledge of the horizontal displacement on F-sheet. How can we move forward? I think something we could do is get information about the vertical component of the ice flow. So this is difficult to do, means you need 3 measurements, but I think we can do it. So right now we're using surface parallel flow. Deviation from this surface parallel flow is called emergence or submergence of the velocity, and it's in steady state with the local mass balance. Right now with a mix of we could do it with a mix of ascending, descending, and right and left sensor. We mix 4 observations, which is complicated to do. Or we could do it with a constellation of satellites that fly information. And in this case, we would need a mix of ascending, descending, and multiple line of sight from this constellation. And this is what Harmony, Earth Exploration Candidate, would do. So here is a sketch view of how it would work. I'm sure you've seen on Monday the presentation on Harmony from Paco Lopez. So on the right, this is the classical view of where you get two line of sight from ascending, descending with classical star system. With Harmony, where if you have two companion, two passive companion flying with Sentinel-1, you can actually get more line of sight for each pass. And if you get the two companion close information, you can get a single pass interferometry where you get actually the DEM, so 4 line of sight with the DEM. And with another way of looking at the ground, so the stereo mode, you would get actually 6 line of sight. So you have plenty of line of sight to retrieve the 3D motion of the ice. This will obviously help a lot for 30 seconds. Help a lot for many applications. So you could evaluate more precisely the surface mass balance, because emergence turbulence velocity should be in a steady state with local surface mass balance, but also surface processes that are happening below the ice, linked to the subglacial water system, for example. And here's my conclusion, and I stop here because I think I'm too.
Thank you very much, Jeremy. It's most likely a bit my mistake that we slightly shifted.
No worries.
The last speaker for this session, and then we will take the question, is Pietro Milello, speaking about Sentinel Tandem X, Cosmos Skyme, and second generation synergies for cryosphere monitoring.
All right, thank you. Can you hear me?
Yes.
Perfect. I'm going to share my screen now. Okay, I hope you can see my screen. This is great. Thank you for having me today for this oral presentation. And this is the last talk for this session. And we've been looking at and listening to many talks that talk about synergistic approaches, including different sensors with different wavelengths and different characteristics. Here, I will talk about the work that I have been doing with Sentinel data, Tandem X, and Cosmos Skymed. And the general message here is that when you sum 3 sensors, the sum of these 3 sensors is not 3, it's more than 3. And I will try to describe in 15 minutes what is the added value of working of these sensors that monitor different variables of a glacier at the same time. We started with the grounding line with Yara. I would like to continue and with the grounding lines as well. So the idea here is the grounding line is an elusive boundary where the ice detaches from the bed and becomes a float in the ocean. Here we have this classical view. This is a video from ESA where we have warm water melting the glacier from the bottom, and because of that, the grounding line retreats. But because the bed of the glacier, as you can see in this video, lays on a reverse slope, we have the so-called marine ice sheet instability hypothesis. And here I'm just giving him some reasons why this is important, and we all know this information is probably, and we know that Antarctica contributed to sea level rise by about 3.3 millimeters per decade during the period 2003-2013, and has the potential to raise the sea level by 58 meters if all the ice melts. In particular, if you look at the Amundsen Sea embayment, we have 1.2 meters potential sea level rise, and glaciers like Great glaciers account for 1/3 of the mass loss from the Amundsen Sea embayment. The reason why I want to focus on this is because when we look at grounding lines, Sentinel currently does not work in that area. So these are key findings. Here on the right side, you can see a time series of Tandem X DEMs that you can read the full paper and Science Advances we published 2 years ago. So what we found here is that there are some physical phenomena, some physical processes that current models do not take into account for, such as models have a fixed grounding line. It doesn't change with tides. And instead, we did find that the grounding line migrates over a range of 2 to 4 kilometers. And this is not a grounding line anymore. It's the grounding zone, as Yara was telling us before. Also, we do find the melt rates at the grounding line that are 2 to 3 times higher than those of the models. Specifically, models do not predict melting at the grounding line. Here, this is an idea. Here, I want to show why monitoring the grounding line frequently is very, very important. So here we have an example of Pine Island glaciers. You can see that my pointer, on the right side, we have grounding ice. On the left side, we have floating ice. And here we have grounding lines from Rigno et al. In 2014. And you do see that if you acquire data at low tide and you compare with the grounding lines measured in 2011, there is almost no retreat. Whereas over Pine Island here, if you acquire data at high tide, in fact, you do see some retreat. And we do have, when we go on, what kind of variables we look at? We look at the velocity. Jeremy talked about it extensively in the previous talk. We can also use mass conservation bed, and Roman explained it also as well. And then we have, of course, tandem X surface elevation change. So here, just summarizing, when also we do have ISAT and we do have tandem X for surface elevation changes. And here I'm plotting a preliminary time series with tandem X. Tandem X, of course, provides a differential DM, so we do need to tie down this time series. And for doing that, we use ISAT2. But when you look at ISAT2, I would like to underline this detail. If you see, look at this arrow, you can actually map this very small lake at close to the grounding line that fills up and drains depending on the time of the year. Now, if you look on the left side instead, you have a surface elevation change map from tandem X, and you can compare different periods, 2011, 2017, and you do see how also I'm plotting here grounding lines from ERS and Cosmos SkyMed. You can kind of underline where that there has been some retreat, and you can actually see it in the DM. But again, using the interface is the method that is most accurate for mapping grounding line retreat. ESA built a legacy in terms of mapping the grounding line. For example, when we look at Pine Island Glacier, for instance, we do have grounding lines mapped since 1992 up to 2011. And this is very important because this allowed us to map long-term retreats over all the most important glaciers in Antarctica. And ERS at the time had a short repeat time compared to Sentinel nowadays. And also right now we can use Sentinel images. This is a quick and dirty movie that I created with Google Earth Engine. They just we can use the amplitude to map cracks or to monitor the size of the ice shelf, because we know when there is a crack, and if you remove an ice shelf from a glacier, this would cause a speed up, which will increase the flux. And what do we need for measuring the flux? Well, we need grounding line measurements. That's why this is another argument why measuring grounding lines is very, very important. This is the results of ERS of 20 years of acquisitions. What happened after 2011? What can we do? We do have an incredible amount of data. At the time when these data have been processed, they were invaluable to understand the dynamics of the long-term dynamics of Pine Island Glacier. And now I will show you 20 years of data, and I will compare it to 1 year of Cosmos SkyMed acquisition. So these are all the data, all the grounding line measurements acquired with the ERS, and this is 1 year of Cosmos SkyMed grounding line data. So you can see that the difference is stunning, just because you're just looking at a newer sensor, higher resolution. But the idea is that, okay, now we can map the grounding line and the grounding zone with the dashed line. What do we do about this data? And if you remember what I said a couple of slides ago, the idea is to improve models, to provide ways and give hints and guide the models to include these physical mechanisms that characterize the physics of the glaciers. And here, if we want to compare Sentinel, C-band and X-band, we know that Sentinel has a 6 days repeat time and Cosmos Chime has a 16. CSK has a repeat time that goes from 1 day to 16 days. And these data have been acquired during the same, almost the same dates. And what happens is that if you need to be careful when mapping the grounding line, because if you map the grounding line here and this area is actually decorrelated, you will end up making a mistake mapping your grounding line. So you do really need to very coherent and high quality interferograms. And now everybody's asking what's going to happen with the L band. 6 days with Sentinel doesn't work, and these most important glaciers, the Amundsen Sea embayment, which because of aliasing problems, changing property of the ice, what happens with the ALS 13 days? Well, if you want to know more about what happens at the L band, you should attend the poster this afternoon. And my coworker and friend Ben Shawhill will present about it, will provide some information about what happens at L band. And also, I can give you also some hints, like getting some ALOS 2 acquisitions in 14 days will also can give us some ideas of what how NICER will perform over this area. So here I'm just giving some food for thoughts in terms of what can be done and what we will be able to do. This is an idea, an overview of the Siager virtual constellation. We do have actually 6 satellites from Cosmos Chime, Cosmos Chime second generation. We do also have 2 SAOCOM satellites orbiting the same orbit. We'll be very curious to see what happens with 8 days temporal baseline. And the idea is that with the CSK second generation, we do have 2 one-day pairs that would actually improve further our capability of monitoring grounding lines everywhere in Antarctica. Again, what do we do here? We were able to task acquisitions even 6 hours apart, and here we can see how we can even map water infiltrating upstream the grounding line at Pine Island Glacier. And for instance, if you start doing some data analytics, you can actually map and see there is some dependence. And now the idea is that the dependence, we need to assess, is this the bed slope? Do we consider the bed slope? Or we consider, for example, the surface slope. So the idea is that now, thanks to this new data set and thanks to methodologies for processing big data in a short amount of time, like the one Yara presented, we'll be able to characterize these grounding zones and also provide some feedback, some inform the models that then predicts glacier sea level. So in order to recap, let me see. In order to recap, I should be pretty much on time. It is fundamental to monitor the grounding lines for calculating the mass balance. And the short-term acquisitions reveal new insights into the tidal-induced grounding line migration. And we can use this insight to inform models. And then once we have updated the physics in these models, we can actually understand better what is how this physics will affect the future of the glacier. Also, last but not least important aspects is the role of international collaborations, which are fundamental for the success of this monitoring campaign. And I would like to say, I would like to thank my co-authors here from all over Europe, from University of California, Irvine, for the German Space Agency, providing the TandemX data from the Italian Space Agency, providing the Cosmos Chime data, and from University of Grenoble in France. And this is actually the core that is pushing this monitoring campaign on and is producing such incredible data and very interesting analytics. Last but not least, there will be a new add-on to this international collaboration, which is the College of Engineering, University of Houston. And since I will be starting a tenure track in geosensing system engineering there starting September, so I will actually like to take the opportunity to advertise some new open PhD and postdoc position. And I think I still have a few minutes left for questions, just in case, but I will conclude here my presentation. Thank you.
Very good. Thank you, Pietro. We take all the questions together now. And so thank you very much to all the speakers for these great presentations. We got several questions. Thank you to the audience for this. Yara, so the first speaker of that session, had to leave, but he did answer, and I will read the answers to the question you posted. So the first question was, Yara, did you compare the neural network result with the resulting phase gradients computed on multiple interferograms? And Yara answer regarding the question about how the neural network captures the correct side of the grounding zone, we do not provide any directional information or mask. The neural network just learn which side is the correct side for subtle differences on the two sides, which is the interesting part. Then it was a second question. And of course, I did actually read the wrong answer for the, sorry about it. So actually the answer for the question, did you compare the neural network result with the resulting phase gradient was, he probably maybe didn't answer to this one actually. So then it was a question about is any manual correction necessary after processing? Also, the nearly 6,000 training and reference imaging, are they manually delineated? Your answer, we do not do any manual correction. Instead, we compare the result with manual delineations to test the performance of the network. Sorry for the lack of clarity. And yes, the training images were manually delineated. I hope that was clear enough. Then it was several questions to Thomas, but Thomas, maybe you take this, you will probably read better the question than answer better, of course. We don't hear you, Thomas, you're muted.
Okay, there was one question regarding why we are using only data during the winter for the interferometric approach. In principle, for the ice sheet wide velocity map, winter data are needed because during winter, the Sentinel-1 acquisition plan has a special campaign where the complete ice sheet is covered by Sentinel-1 track, and each track is continuously acquired at least by 4 acquisitions. And during the summer period or outside of this campaign, we have primarily the margins continuously covered by 6 tracks. And in the recent 2 years, there were some more tracks added by the ice sheet, by the ice sea ice community, which are also doing some acquisitions over the Greenland ice sheet. So therefore, the winter campaign was primarily used for this. Another reason is, of course, that during winter we have a better coherence as there is no melting. In summer, where we have melting in at least at the margins and lower elevations, this will cause the correlation. Then there was one question, I think, by Christoph regarding the sample profile of offset tracking versus INSAR, which is an example to show the performance of the interferometric product against the offset tracking product. And he mentioned correctly that there is a systematic offset of the results. So this first, when you look to the values on the y-axis, so the difference, this bias between INSAR and the offset tracking, this is very small because this the scale was in principle it was given in meters per day, but the difference is in the order of less than the centimeters or a few millimeters. And this is obviously caused by the calibration process, what we are applying on the offset tracking product. And this is in the center of the ice sheet, and the calibration is done at the margins. And we hope that applying the ETAT annotation, this improved annotation, that we can get rid of these ionospheric and remaining tropospheric effects in this. I think these were the main questions, if I saw so far on me.
Yes, thank you very much, Thomas.
Okay,
then it was many questions to Romain.
Yes.
So can you read also and take some of the most important stuff you answer partly already in the chat?
Okay, yes. So I'm going to go through them. So the first question was, how could you justify that your proposed framework has been able to resolve velocities in featureless accumulation zones of mountain glaciers? So yes, so concerning the accumulation zones, really the combination of several sensors and really the use of Sentinel-1 made a difference, specifically in Arctic, where you don't have much features on the top of ice caps, as it was shown for the example of the Penny ice cap. So the use of speckle tracking instead of feature tracking really made a difference there. So then, considering your results on Penny ice cap, I would say the RGI catchment does somehow not fit the patterns you observed. Does the maybe wrong glacier catchment affect your processing? So, so the big difference with our approach is that we use a regional inversion approach. So the RGI catchment does not influence our model. In opposite to what has been done before, previous methodology used a glacier by glacier inversion approach, and along with a 2D profile inversions. So they are heavily relying on the RGI delineation. So yeah, part of the misfit is caused by the can also be caused by the RGI catchment. Okay, how do you weight the different sensor when combining? Can you comment on how you achieve 50 meter when you rely on Sentinel-1 as an important data source given its resolution? So concerning the weighting of the different sensor, this is also time consuming. So we assemble mosaic for each sensor. We compare the mosaics and we attribute the weights manually based on the noise level of each mosaics and their respective coverage. For Sentinel-1, we mainly use the Sentinel-1 for large ice masses. So Patagonia, Alaska, the Canadian Arctic and the Russian Arctic, where the difference in resolution is not an issue compared to optical sensor, as it was shown in previous studies. So another question, because of the ship size versus the spacing used for ice flow estimation, you said in your article that each point in your velocity may not be independent. Is it taken into account when you invert the ice thickness? So when we invert the ice thickness, we only use the composite mosaic at a sampling resolution of 50 meter. So indeed, points may not be independent, but as I shown for two examples in Patagonia and in the Himalayas, there is a great, really improved spatial resolution. We are able to capture much finer details compared to previous mapping. So those velocity maps are already validated using GPS measurements, and I cannot think of any easy way to account for the dependency in between each pixel during the thickness inversion, but we are open to suggestion. Yeah, and the final question, how did you apply the thickness inversion from mass balance model? Does estimation rely on least square inversion using height, velocity and velocity on surface? How did you constrain the inversion with boundary conditions? So the ice thickness are based on the shallow ice approximation that links the surface velocity, the surface slope, and the creep parameter A, and the beta parameter, which is the ratio between the surface and the basal velocity. The A and the beta parameter are calibrated using the in situ thickness data from the glacier thickness database that is publicly available. And I think that was it.
Really good. Thank you so much.
Thank you.
And then I think there is at least one question to Jeremy. Did you say it, or do you want I read it?
No, I can read it.
Great.
Thank you. So there is one question from Rudy Vindliber. With such huge amount of data, how do you check loss velocity product quality, decorrelation, phase unwrapping errors, calibration, and accuracy before matching everything together? So all the velocity or the unwrap phase are calibrated against the speckle tracking map. And this speckle tracking map has been constructed using a region where there is no motion as calibration, and long tracks that would cover from coast to coast for the calibration. So for long track, for example, from NVSat ASA. So there could be some issue. If the speckle tracking map has biases, then they would be reported in the phase map. We checked when it was available the result against GPS measurements, so it shows that the phase map was much better than tracking map. But obviously, if we had more ground control points, it would definitely prove very useful to actually do a better calibration over Antarctica for sure. That's it.
Thank you very much. I don't think we forgot one question, I believe. About the question to Yara, I think his email has been shared now on Slido, so you can directly take contact with him. He will probably take the question in a much better way than the way I did. We're quite in a perfect timing right now, so I think we can close that first session. So I would like to thank you a lot for your contribution. And the second part will start after a short break at 11:30. If somebody has any comments, I see Thomas, are you trying to say something because you're muted? No, okay. Really great. So thank you very much, everybody, and see you in 30 minutes for the second part of the Ice and Snow session.
Thank you.
Thank you, Lee.
Thank you. It's nice to see you guys. Last time was 2017.